You do see the slides now? Yes?
Yes.
Great, thanks. Okay, so hopefully that'll go a little smoothly in the future. It looks like a lot of you guys got kicked out of the meetings when you left your breakout rooms. So I will fiddle with those and make sure it's not something on my end. But quick note about upcoming events before we get into our chemistry review. So basically, the rest of the class is going to work in a similar way. You do have a discussion post due at the end of Monday, just asking a couple things about how this week went. You'll have an individual reading quiz due, and then we'll have a problem set in class. The dates on this upcoming event slide might be off, but they're in the calendar on Brightspace. Okay. So our main topic today is a short review of chemistry as it pertains to our study of cells. So here's a short little GIF, right? You have someone dipping their fingers into a beaker with a powder on top. And we see that their fingers are actually remaining dry and covered in powder, not covered in the liquid. This doesn't happen with all substances, but this is kind of one of the things we want to be focusing on as we're thinking about chemistry here. What we really want to know is how different atoms, different molecules are going to interact with water, because water is going to be the main environment for our cells. It's going to be what surrounds our cells. It's going to be most of what's inside our cells. So as we go through today, I want you to keep a careful eye to that. That's the big picture thing that we're concentrating on. Okay. So our four most common elements in living organisms that we're going to be thinking about are carbon, oxygen, hydrogen, and nitrogen. Now, each of these elements are going to be present in some proportion in living organisms. Living organisms are going to be mainly carbon-based, but we are going to see these other atoms in many of our different types of macromolecules that we go through. And of course, there are many more atoms present in an individual person, for example, but in much smaller amounts than these four main elements. When we're thinking about these atoms are the smallest unit of matter, and they build up to molecules. So an atom is composed of a nucleus with protons and neutrons. Here, what we want to think about is that those protons are positively charged. It's surrounded by a cloud of electrons. Now, electrons are negatively charged, and electrons are a thing we really want to be careful about thinking about as we go through this course, because we'll see, especially when we get to metabolism at the end of this class, we're going to be talking about how molecules pass electrons back and forth. Okay. So we have two regions. We have three subatomic particles, the electrons, the protons, the neutrons. Nucleus in the middle with the protons and neutrons. Outermost region has electrons, they're orbiting around. Protons carry a positive charge, electrons carry a negative charge. Neutrons are not charged, so honestly, in this course, we really don't have to think about them at all. Usually, we're going to see that the number of protons and electrons are balanced. So most of our atoms in their normal states are not going to have a charge because they'll have even numbers of positive protons canceled out by negative electrons surrounding that atomic nucleus. Now, in biology, we care about bigger things than atoms. So what we really want to understand is how atoms link together to make molecules. Now, they do that through bonding. We have two main types of bonds, really strong interactions, ionic bonds and covalent bonds. Now, I assume you have all covered this in chemistry. So chemistry is a prerequisite for this course, which is part of why this review of chemistry is really fast. If you have not had a chemistry course yet, please get in contact with me. We'll need to sort that out. Okay. So strong interactions, we have ionic bonds and covalent bonds, and we'll look at a couple of the differences there. We have weaker, more temporary interactions called hydrogen bonds. which are actually really important for biology, which is why they're highlighted here on this bonding slide. So now we're going to compare these different types of bonds. So we're going to start with ionic bonds. So in ionic bonds, what we have depicted here, right, we have our atomic nucleus, tells us which atom that is, which element it is. So here we have sodium and chlorine. And here we have depicted the electrons that are in the outermost shell of the atom, so farthest from the nucleus, the ones that are going to interact with other atoms. We would call these valence electrons. So sodium happens to have 1. Chlorine here has 1, 2, 3, 4, 5, 6, 7. In general, an atom is going to want 8 electrons in its outer shell. The exception is the innermost shell, which only holds 2 electrons. Okay. Most of our atoms that we're talking about, they need 8 electrons in this outermost shell. So in an ionic bond, the way this happens is that one atom donates an electron to another atom, filling the atom that had more electrons in that outer shell. It's now full when this purple electron from sodium goes over to the chlorine. It's now full. It has a full 8 in its outer shell. Sodium would drop down to its next shell, so it would also have a full outer shell, or we could see that as 0 in this outermost shell here. Now, the reason we care about ionic bonding in biology is that ionic bonds tend to dissolve in water, creating things called ions. So what we see here on the right, you can see we see sodium has a plus, we see chlorine but has a minus. So this is a sodium ion and a chloride ion, and ions are charged. Sodium is positive because originally sodium had balanced numbers of positive protons in its atomic nucleus and negative electrons in the orbitals surrounding it in that cloud of electrons. When it gives away an electron, right, it's subtracting a negative. That means basically that those positive protons in the nucleus can kind of shine through, right? It now has more protons than it has electrons, so they don't cancel out anymore. So it's positive. Chlorine gained an electron. Electrons are negative, so it's now negative. We call these cations and anions, although we're not going to use those terms very much in this course. We have positive ions and negative ions, and this is going to be important when we think about how they interact with water. So the formation of an ionic compound, an atom is losing an electron, another atom is gaining an electron. One way to tell that something's going to form an ionic compound and then form ions is that one of our atoms is going to be a metal, and our other atom is going to be a non-metal. And we can tell this from looking at the periodic table, or knowing our atoms, or Googling it. In this course, except on things that I tell you are closed book, by the way, so exams are apart from this, but all the problem sets and stuff, you are welcome and encouraged to use good sources. So whether that's a textbook, whether that's Google, those are fair game. Don't copy anything wholesale. Like, I can tell if you copied a paragraph out of a textbook, but looking stuff up, totally fine and expected. Okay, so if you have to Google is blank and a metal, that's fine. Okay, so each ion is then charged because the one atom lost an electron and becomes positive, the other gained an electron and became negative. In covalent bonds, we have something different. Covalent bonds, electrons don't get donated and accepted, they get shared. So here we have oxygen, we have hydrogen. Hydrogen is one of our special cases. It doesn't have very many electrons, right? It's just got this one here. So this is our innermost shell that only needs 2 electrons. Oxygen has a normal shell that needs 8. Okay, so when hydrogen interacts with oxygen, instead of hydrogen giving up its electron, it shares it with oxygen. So you can count it towards hydrogen and towards oxygen. And oxygen shares one back. So we can count that towards the hydrogen and oxygen as well. So that's what we see happening here. So hydrogen and oxygen are sharing this white one and this red one. In order for oxygen to have a full outer shell here, it actually needs one more. It can't just share this one with hydrogen, so we need another hydrogen. Hydrogen is satisfied with just this one bond with oxygen because it's only displaying that inner shell that only needs 2 electrons. So this is the formation of water. H2, because we have 2 hydrogens. O, that's our oxygen. It's stable and water sticks together because they're sharing electrons. So those electrons have to orbit both atomic nuclei, so they stick together. So a covalent bond will not fall apart in water because they're sharing. Helpful for this class, because this is not a chemistry class, this is a biology class, is instead of doing a lot of counting with the periodic table about how many electrons each of these atoms have, because we keep talking about the same atoms over and over again, you can shorthand it and just kind of memorize the number of bonds it'll need to form. So here, hydrogen just needs 1 shared electron. So hydrogen will form 1 covalent bond when we see it in a molecule. Oxygen needs 2 more electrons. So oxygen is always going to need to form 2 bonds in order to reach that stable state. Okay. So 2 or more atoms can bond together to form a molecule. 2 hydrogens and oxygens share via covalent bonds. That makes water. Okay. So this is just circling, sharing, saying that they're stable when they're sharing like this. They have to stay close to each other in order to keep sharing. Okay. So in each single bond, we just see 1 pair of electrons. Each atom is sharing 1 back and forth. Hey, sorry about my dog. Okay. And this is all in your slides, and these are just notes. You don't have to copy everything down word for word. This is kind of just for explanation. I'm not going to be quizzing you on this particularly directly in the future. You should know that double bonds can form. So when we have oxygen in the air, it's 2 oxygen atoms bonded together into a molecule. And the reason that happens, right, is each oxygen is trying to find an electron to share here. It's trying to find an electron to share here, right? It needs 2 more electrons. So it's looking to form 2 covalent bonds. If it runs into another oxygen atom, great. That oxygen atom also is looking to form 2 bonds, 2 covalent bonds, share 2 electrons. So we can create a double bond between these 2 oxygen atoms. Totally allowed. We'll see that with oxygen with some regularity. So here we see 4 electrons in total are being shared. Okay. That brings us to polarity. So the concept of polarity is really important to biology, partially because water is a polar molecule. It contains polar covalent bonds. Now, what a polar covalent bond is, fundamentally, is that electrons, even when they're shared between 2 atoms, they may not be shared totally equally. The atoms are actually orbiting, right? They're actually moving around. So they may spend more time, get closer to one atomic nucleus than another, which means that basically we have like a little bit of a charge on that atom, so on that portion of our molecule. And that's what a polar covalent bond is. We can think about it as being like a little charged. It's not a full charge, but we got a little bit of charge there, which is going to affect how it interacts with ions, which do have charges, right? Because they donated and accepted electrons. Okay. The way we tell that a polar covalent bond is going to happen is we look at electronegativity. So this is another thing you can pull up, an electronegativity table. But again, this is a biology class, so for a little shorthand, we can remember that oxygen it is highly electronegative, and specifically it has higher electronegativity than hydrogen, which means that oxygen is going to be pulling those electrons closer. You're going to spend more time with the oxygen, which means that the oxygen is going to have a weakly negative charge on it. All right. So if we were to draw it out, here we've drawn out our oxygen atom, we've drawn out each of the hydrogen atoms. So in certain situations, we're going to want to indicate that we have little bitty negative charges here on our oxygen because the electrons are spending more time there. We have little bitty positive charges on our hydrogens because the electrons are spending less time there, which means that positiveness of the protons kind of shows through, okay, because they don't always have those electrons to balance them out. Okay, so this is a fundamental part of water. This is a lot of why water behaves the way it does. The fact that we have these weak negative charges on oxygen, these weak positive charges on hydrogen, which we call a polar covalent bonds. This is really why water can dissolve ionic bonds, is because these weak charges interact with the charges on the ions. That's why water can pull them apart. Okay. So here we have an electronegativity table. So here in green, we have low electronegativity. In red, we have high electronegativity. Okay. So if we were thinking about our water, right, we can see that our electronegativity for hydrogen is in this yellow range. We got a 2.1. Oxygen here is higher range, 3.5. It's red, right? So if we compare them, we can see visually with these colors that oxygen is more electronegative than hydrogen, which means it's going to kind of hog the electrons. Another thing we might note, because we care about a very small number of atoms in this course, right, we're also going to want to compare the oxygen to carbon. And we can see that there's also a little bit of a difference there, right? The oxygen is more electronegative than the carbon, which is why, on the whole, when we're looking at these molecules, we can mostly think, if you see an oxygen, you should immediately start to think, oh, okay, there's probably a polar covalent bond there. Okay. So this is just showing that water molecule again, weak positive charge on the hydrogen that doesn't have as much electronegativity as the oxygen. So this is the key to water, these polar covalent bonds. Oxygen, with its slightly negative charge, slightly attracted to the positive charges on other hydrogens in other water molecules. Okay. So another fundamental principle that we want to remember, right? Positive charges and negative charges are attracted to each other, right? That's why when they're not in water, when we have ionic bonds, right, we might form like crystals, right? Because those charges are attracted to each other. Reason the ions are dissolving in water is because they are also charged, so it messes up that system. Okay. So when we have a beaker full of water, we have polar covalent bonds between oxygen and hydrogen in a single water molecule. But when we think about all our neighboring water molecules, we have a hydrogen bond. So that's weaker. They're not sharing electrons. They're just attracted to each other because of that kind of magnetic property between the positive and the negative. And we can think of those as kind of magnets. Okay, so this is just showing the hydrogen bond between two neighboring water molecules. Oh, sorry, I already told you the answer to this, but you can look at the slide. And I'll pause so you can remind yourselves. This is a covalent bond, specifically a polar covalent bond between hydrogen and oxygen in a single water molecule. But if we have neighboring molecules, We have a hydrogen bond. We draw hydrogen bonds with this dotted line in general, and that indicates to us that they're not a covalent bond. They don't have to stick together. We can separate them. They're not sharing electrons, but they are important to know about when we think about how water works. Okay. All right. So water makes up most of a human body, like 70%. So it's really critical molecule for life on Earth. Right? It doesn't just make up humans, it makes up all sorts of organisms. It's the environment we're in. We all need to drink water, really important. The reason it has the chemical properties it does, and the reason it has these special interactions with other organic molecules that it does is because it's polar, right? It has those slight charges, slightly negative on oxygen, slightly positive on hydrogen. And because of that, it can form hydrogen bonds, right? In other classes, you'll probably learn a lot about all the neat things water can do with its hydrogen bonds, like create surface tension, have capillary action. We're not going to talk about that right now because we're talking about cells. But this is really important to the way water behaves in life, these basic chemical properties. So here we see a picture of what happens with an ionically bonded compound when it's dropped in water. So sodium and chloride, table salt, ionically bond to each other, meaning sodium gives up an electron, gives it to chlorine. We saw that. If we drop that then in water, because of these full charges on our ions, these little charges on pieces of our water molecule, the atoms are going to break off from each other and form associations between the ion and the water molecule. Now you'll note that those water molecules are associating with the ions in specific ways, like they're positioned differently between the chloride ion and the sodium ion. So here, the chloride ion, we have hydrogens touching the negative chloride ion. That's because hydrogen is slightly positively charged. So those slight positive charges are attracted to the negative charge on chlorine. We have the reverse happening on sodium because sodium is slightly positively charged. So it's attracting those slight negative charges on the oxygen. So this is analogous to what's happening when we form those hydrogen bonds. We can kind of lump them all in the same bucket in our minds. We can think of these as basically hydrogen bonds, although maybe don't tell a chemist that. But it's working the same way. We just have attractions between these charges, right? This little negative on the oxygen and this positive on the sodium means that the oxygen is going to be next to the sodium. I'm telling you this because I'm going to ask you on your problem set to draw stuff. Basically, the question about ionic bonds, you want to draw something like this. Okay, so water has solvent properties because ions dissolve in water. Polar molecules also dissolve in water. So polar molecule is one that includes polar covalent bonds. And when we say it dissolves in water, we don't mean that those covalent bonds break. What we mean is that those pieces of our polar molecule that have slight charges are attracted to pieces of the water. So just neighboring molecules would kind of spread apart. Okay. So ions and polar molecules, because they dissolve in water, we call them hydrophilic. Philic means like loving in Greek. Hydro means water. So hydrophilic, water loving. Non-polar molecules, which are ones where we just have normal covalent bonds. So like if you have a molecule where you only have bonds between carbon and hydrogen, if you flip back to the electronegativity table, both the carbon and the hydrogen are yellow. They have really similar electronegativity. So the bond between them would not be polar, just your basic run-of-the-mill normal covalent bond. When we see that, neither of the atoms have charges in these nonpolar molecules. So these nonpolar molecules are not going to dissolve in water. They're gonna stick to each other. We're gonna call them hydrophobic. So phobic, like a phobia. They're fearing the water. They stay away from the water. They just want to associate with themselves. When we talk about these ions, these polar molecules, when we talk about stuff dissolved in water, look at the solve part, right? Water is the solvent. It's the thing that dissolved it. And we'll refer to the compounds that are dissolved or sometimes just mixed into the water as the solute. And we're not going to talk about that much today, but when we start to talk about cells and what's inside and outside the cell, this is going to be relevant that we can keep track of solvents and solutes. So you'll see these terms again. And we'll talk about hydrophilic and hydrophobic a lot. So if we look back at this GIF from the beginning, we see this powder. This guy's sticking his hand in the powder. It doesn't get wet, still just covered in powder, totally normal. We will actually be able to predict the properties, the chemical properties, even the types of bonds that the molecules that make up that powder have, right? This is specifically lycopodium powder. I think it comes from like the spores of mushrooms or something. But what's going on with that powder is that that powder is made up of non-polar molecules. So they're non-polar. The atoms don't have any charges on them. So they're not dissolving in the water. They're hydrophobic. They're repelling the water. Okay, so that's why you can't get through. Right? They really, really don't want to mix with the water. And that's going to be important eventually when we start to talk about how our cell membranes work. Okay, so we're going to break up now and we're going to start working on our problem sets. So you can go ahead and open those up as I start to kind of explain to you what we're doing. But if you go to the week 1 under the content tab, you're going to see a chemistry problem set multiple choice, a chemistry problem set free response. And when you go into the chemistry problem set free response, it'll link you to this Google document. Okay, so the first part of the first part of this problem set is going to have some multiple choice questions. And then the second part is the free response. So this is the document you're going to copy and work on together. So it's going to ask you to write out some answers. And we're also going to be asking you to draw some molecules. Okay. And pay careful attention to the instructions. So if you're drawing a covalently bonded molecule, you're representing covalent bonds with straight lines, pairs of shared electrons. I want you to circle and label functional groups you can identify. Functional groups are specific configurations of atoms that we'll see repeatedly in different types of molecules, and you have a table of them below. So after you draw your molecule, check through this table and see if you see any of these functional groups. When you draw an ionically bonded molecule, you're going to want to draw how the resulting ions interact with the water. So check back in the slides to that image of the sodium chloride in water and draw in those hydrogens and oxygens and how they're orienting relative to our ionic compound. Okay. Here are the 3 molecules that we're asking you to draw. Okay. And then here's another kind of short discussion question you'll answer. In the slides, I have some directions on, and I just put these in, sorry guys, if you printed them out, and just pull these up again. These are how you can draw together, right? We do want you to work together, and especially when you're annotating together in Zoom, when I pop into the breakout rooms, I can then see your screen, which means number 1, I have something to talk to you about, which I love. But number 2, I can tell if you're doing something that's kind of off, and I can kind of steer you towards the right answers if I can see what you're doing. Whereas if I go into your breakout room, nobody has the camera on, nobody's talking, and you're all working independently. Unless you ask me a question, there's no way for me to help you or figure out where you need help. So I do want you to practice sharing a whiteboard and drawing together. It'll also make it just kind of go faster since you're working on this problem set together and you're just going to submit one problem set for the entire group this time. Okay, so here you can find how you can annotate. It'll allow your group members and you to draw on the screen. I also have instructions on how you can save drawings. You can either do that from within Zoom, or I use this probably every 20 minutes in my own life. On a PC, there's a snipping tool. It just lets you select parts of your window and then it's immediately in your clipboard and you can paste it into any document. And I hear there's a similar tool on a Mac if you press Command-Shift-4. Okay, and here are some more tables at the bottom. Functional groups, electronegativity table, table telling you what is a metal and what isn't. Okay. Questions before I send you out to work on that problem set? Yeah, go ahead, Carter.
So there's two different assignments. There's a multiple choice and a free response.
Yeah, there's a multiple choice section and then a section where you'll upload this assignment document.
Okay, thank you.
Yep. All right, I'm gonna send you out to groups and then I will be popping around as you guys need help. But if you need immediate help, just call me. I think there's a button in the breakout rooms.